This is our second lecture on concept of stress. I'll start this lecture by discussing the symmetry of stress tensor. The symmetry of stress tensor is proved by considering the principle of angular momentum. And here we'll take the moment balance about an axis parallel to x3 axis and passing through the centroid, center of the cuboid. So here in this picture, if we see this axis passing through the midpoint to the midpoint of the bottom face. So along this line, we are considering the moment balance. So here if we see the stress components, those are having 3 as an index will not produce any moment because they passes through the axis. So these are actually passing through this axis, so that's why momentum is 0. Whereas the other components like sigma 2 1 1 2, so they will have a moment arm, so they will produce moment. So that's why as this third components, the stress components with 3 as an index, as they are not producing any components, so we are very well take instead of the cuboid in parallelepiped by showing just this plane perpendicular to this x3 axis. Okay, so those components only we can show and see how this moment balance can be done. So this is done here, so that's why there is a differential parallelepiped zone. And here we are not considering a uniform state of stress all through the body, so that's why there can be incremental changes. So we can see this edge and this edge, they differ, and their distance between these two will be delta x1. So, and delta x1 is considered positive from left to right. So that's why this right hand side stress components will have an increment as per Taylor series expansion, and the first term is considered here. So this is this first term in the equation which I have presented for proving the stress symmetry. There I have considered this is as delta sigma 2 1. So this entire thing is considered as delta sigma 2 1. And you can see this sigma 2 1 and sigma 1 2, they give a counterclockwise moment. And if we consider the sigma 2 1 as a stress, then total force will be stress times the area, and area of this face is delta x2 times delta x3, because delta x3 is the perpendicular distance. And then we are taking moment about this midpoint, so axis passing through the midpoint, so the moment arm to each of these components will be delta x1 by 2, and it is counterclockwise, so consider as negative. So now we can see the equation what we have obtained here. We can see this negative sign is for the counterclockwise moment, and then the force is sigma 2 1 times delta x2 into delta x3. Then this is the moment arm. This is for the left side force, and then the right side force has an incremental value, and then This is the area and multiplied by the moment arm. So similar thing is done for the other component sigma 1 2 and the sigma 1 2 plus delta sigma 1 2, and there can be some additional body moment. So this is the moment acting on the entire body. We can think of this similar to body force when we consider linear angular momentum balance. So in general, this body moment will be absent. If we have some moment like field where this body moment can experience like in space or somewhere, so this may come, but in practice we will not have this body moment, and this total moment then will be equal to I alpha, where alpha is the angular acceleration, I is the moment of inertia. Uh, then we will see what is I here. So I for uh, like a cuboid about the 3 axis or x3 axis is this one. So you can refer any textbook, you will find that. And if we assume that there is no body moment, so this is the typo, it should be body moment. And if we consider the higher order terms to be 0, then we will see this above equation will reduce to the simple form. And then from there we'll get sigma 1 2 equal to sigma 2 1. So similarly, if we consider moment balance about x1 axis and x2 axis, we'll get this other two relations, and therefore you can write that sigma ij will be equal to sigma ji, considering the angular momentum balance, and the stress will be considered that it's a symmetric stress tensor. So here one thing I just would like to point out, the handout what I have sent, there was some difference here. So again, that was also a typo. You just make a note of it. So there is some change earlier in your earlier notes. It was sigma 1 2, but it should be sigma 2 1. All right, so consider proving this stress is symmetric. Now we'll move to different like discussion on the normal component of stress and shear component of stress. So this, you know that if I have a body cut through a plane, then on that particular plane, if I choose different point, then at that particular point, depending on the normal vector, we'll have a traction vector. So let us say this is the point and this is the point and this is the plane, and then the plane has a normal vector n, and if we consider the stress tensor, then sigma n will give you the traction vector, and this traction vector can be in any direction. So that traction vector can be split it into two components, one along the normal vector, which is denoted as Tn parallel to normal vector, and then another component will be a along the vector perpendicular to this n. So this is denoted as M vector. So this is the component Tn perpendicular. So the component which is along the normal will be called as the normal stress, and the component along the tangential direction will be called as the shear stress. So that's why that's how these two stress components are defined, and we can see that the normal stress will be if that is the magnitude of the stress is positive, then it will be called as a tensile stress, and when the magnitude is negative, then it is called as compressive stress. So tensile and compressive depending on the magnitude of the stress. So that's actually because this sign is important. The material behavior will change if the normal component is positive or negative, because the tensile stress will try to pull the material apart, whereas the compressive stress will try to squeeze the material. Uh, so they had actually different behavior. Whereas the shear stress actually, whether it is positive or negative, they have the same behavior. It will try to shear off the two surface. So the positive or negative actually will alter if I have a different coordinate system. So that's why sign of shear stress is not that much important as compared to the sign of normal stress components. All right, so now sigma, you know that sigma is the component of the traction vector along the normal vector. So that's why we can find that sigma as n dot t, and t is sigma n. So n dot sigma n. In matrix form it is n transpose sigma n. And then if I want to find the vector sigma, the normal stress vector, so that will be the magnitude n dot t along n vector. And then this shear stress vector is traction vector minus the sigma normal vector, because the traction vector is the sum of these two. And then if I want to find the magnitude, so it is traction vector square minus the normal vector square, and the square root of that. And this is t dot t minus sigma square. Sigma square we have already got, it is n dot t. And the t dot t is sigma n transpose times sigma n in matrix form. And that we are considering sigma as symmetric, so it is n transpose sigma sigma n. So this is some formula you can remember when we would like to compute the normal stress component sigma and the shear stress magnitude tau. Okay, so we can have one example. Let us say there is a body which has the stress state at a point like this, and then we want to find the traction vector and the normal stress component on a plane that passes through the point, that particular point where the sigma is defined, and the plane is parallel to the plane defined with this. So this is the equation of plane. So we should cut a plane parallel to this plane passing through that point, and then at that particular point then we want to find the traction vector. And then later on we also want to find out if we change the basis vector. So this sigma is defined using basis vector ei. So now if I have a prime vector, prime basis vector, prime system, then how this sigma 1 2 components will look like, 1 2 prime will look like. So that's the next part, second part. All right, so now to find the traction vector, we know that we need normal vector. We have already sigma defined, so if we find the normal vector n, then we can find traction vector t as sigma n. And to find the n uh, perpendicular, like it's if there is a surface equation of surface, then the normal vector is defined as gradient f by the magnitude of the gradient f. So gradient f is the a vector normal to the surface at a particular point, and then if you want to make unit vectors, and you have to divide that vector by the magnitude of that vector. So if, as this is an equation of plane, so that's why everywhere you will get same normal vector to that surface. So that's why the n will be not a function of x. But if I have a very complicated function, then you will see that this normal vector also will be a function of the space, and it will change if I change different points. But here it is not a function of space. All right, so if the normal vector is obtained, and then the traction vector is found out using this relation t equal to sigma n, and that's the magnitude we got. And then the magnitude, this is the traction vector, and then the magnitude of the normal stress will be obtained as n dot t. So this is calculated as n transpose t. This is the magnitude. And then prime components, we have to use this relation, that sigma ij prime equal to ei prime dot sigma ej prime. So you remember that we had the transformation of stress tensor, and how we can find the prime components of a tensor that we discussed. So aij prime equal to ei prime dot ej prime. So that's the formula we had. All right, if we use that formula and then put all these vectors in particular place, we'll be getting that prime components. All right, so now principal stress and principal direction. So we have discussed what is principal values of a tensor. In the similar direction, here also we can get the principal stress and principal direction. So that they're the same concept, nothing changes here. So as we have discussed that, I think I will not spend much time on this. Where stress is a second order tensor, we have discussed for a second order symmetric tensor how the eigenvalue problem is discussed, and the principal values of the tensor is also discussed in detail. All right, so here you can see for this eigenvalue problem of the stress tensor, sigma n is lambda n. N, if n is such a vector, when it is acted by the tensor sigma, it will generate a vector parallel to that n. So that's the statement of the eigenvalue problem, and from there we can find this characteristic equation, and then by solving that we can get the three principal values sigma 1, sigma 2, sigma 3. For the stress tensor, we will call this roots at sigma 1, sigma 2, sigma 3, and these are the principal stresses. Here the invariants, stress invariants I1, I2, I3 can be also expressed in terms of the principal values of this. So this is also discussed if you refer the discussion in the first chapter. We have given more details on this. The formulas, everything are given there. And here, so sigma 1, sigma 2, sigma 3 will be called principal normal stresses or simply principal stresses. And as we know that as sigma is symmetric, the eigenvectors will form orthogonal basis vectors. And the eigenvalues also will be real. And this orthogonal set of basis vectors will be called principal directions. And their related normal planes will be called principal planes. So the planes which for which the normal will be along the principal direction will be called principal planes. All right, so now we can see that for each of these principal planes, we'll not have shear stress. So there is a question that does principal planes have shear stress? The answer is no, because the traction vector, as per our definition, sigma n is my traction vector, and that is if that is a principal plane, that this sigma n will be equal to lambda n. That means the traction vector is equal to lambda n. So that means it is parallel to the normal vector. So that means the traction vector will not have any shear components. So it will have only normal components. So no shear stress on principal planes. Now we will see what are the extremal values of the normal stresses. So this can be proved in three methods I have given. So this is based on Lagrange multiplier method. So this is this is a pretty much mathematical, but if you look at these equations, you will get to know it. So I'll just explain one, which is the second one. This you just go through yourself, you will find out no issues. So method 2, which is actually discussed for both normals, extreme values of normal stress and shear stress. So this is a common method applied to the shear stress also. So let me discuss this a little bit. So here, let us say we have n1, n2, n3 as the principal direction, and as they form an orthogonal basis vector. So this basis vector will consider to represent the sigma, the stress tensor. So with this basis vector, we know that the stress tensor will be diagonal. So that also we have proved. So if I just take one image here, you'll see what we are talking about. This orthogonal basis system along the principal direction. So if we have a general basis system, then the stress components will have will be represented by this. So we'll have all stress components, the normal stresses and shear stresses. But if we change the coordinate system or rotate this coordinate system suitably and align that basis system to the principal direction system, then we'll see that the representation of the stress components will be simplified. There won't be any shear stress components. We'll have only normal stress components, sigma 1, sigma 2, sigma 3. So this is what shown in this right hand side figure. So we'll work because this is the same. So we are dealing with the same stress tensor, but we are just changing the coordinate system. So that's why the physical significance of the stress remains same. So we are just having a different coordinate system to represent that same stress tensor, and this will make our life a little easy because we will have only three scalar values, sigma 1, sigma 2, sigma 3. And then let us take some arbitrary plane with respect to this principal directions, and that associate unit vector of that plane will be m hat. Then m hat will be expressed as components of this three basis vector n1, n2, n3, and those components are denoted as m1, m2, m3. So m is m1, n1 plus m2, n2 plus m3, n3. So this is the arbitrary vector. And then on that arbitrary plane, if we want to find the normal stress, then that sigma on m, sigma m is equal to m dot sigma m. So this sigma m is the traction vector, and then plotted with the normal vector will give you the normal stress component. So that if we calculate, we'll see that will turn out to be this. So this is my normal stress component. And now we have to see what is, so you can see for a given sigma 1, sigma 2, sigma 3 state of stress, the normal stress component is a function of this m1, m2, m3. So now we have to see which m1, m2, m3 will give you the sigma to be maximum. So but here one thing is that there is a constraint on m1, m2, m3 because m should be an unit vector. So so that's why m1 square plus m2 square and m3 square equal to 1 will be as a constraint. So it's a constraint optimization problem. So we have to find the extreme values of m, sigma m, with respect to the variable m1, m2, m3, with the constraint m1 square plus m2 square plus m3 square equal to 1. So this problem can be simplified using this method. So m1, we just using the constraint, we replace one variable and make it a function of two variables in this manner. So let us say m1 square equal to 1 minus m2 square minus m3 square, and that you put in sigma m equation. Then we have this equation. Now sigma m is a function of m2 and m3. So we have already considered the constraint equation. Now for extreme values of sigma m, that the partial derivative of sigma m with respect to m2 and m3 should be 0, and that gives this relation. And here you can see for general case sigma 2 is not equal to sigma 1, so that means m2 should be 0 and m3 should be 0. So when m2 and m3 should be 0, that means m1 is 1. So m1 is plus minus 1. So that is the solution. That means the plane is along the unit vector n1, so along one principal direction n1. So now we have taken n1 as an arbitrary direction. So we can change the variable suitably, and we can get the optimum plane is along n2 and n3. So that means the principal planes are the planes where the normal states will be maximum or minimum. So maximum and minimum values of normal states will be along the principal planes. So that's one important observation. So you can see that we have three uh, principal values or three principal stresses for this three-dimensional state of stress: sigma 1, sigma 2, and sigma 3. And then these three will be the extremum values. Okay, so that means one is the maximum one, another is the minimum one, and the middle one is also a local extremum. So that means it's a local minimum or maximum. So that's one important thing. In two-dimensional case, it was quite obvious that one is the maximum value and another is the minimum value. But for this three-dimensional case, we can see that there are three values, and those threes are extremum values. That means one should be maximum and another should be minimum, and the middle one will be also some local minimum or local maximum. All right. So that this one I will demonstrate, not maybe not completely, but partially you can see this one with a Matlab demonstration, which I will show you in this lecture. So method 2 also, I think you can very well understand. This is not that difficult. So this is kind of an indirect way of proving uh, that the normal stress will be maximum along the principal direction. But I think the method 1 and method 2 are the more formal way of proving this. Okay, more mathematical. All right, so method 3 you just look at, you'll understand that. Now let us come the extremal shear values, shear stress, and this also done in a similar way as we discussed for the normal stress. So we are considering again the basis vector along the principal direction, and then take one arbitrary plane with respect to this principal direction n1, n2, n3, and then the magnitude of the shear stress, which is tau m, we have to extremize. So because for shear stress, we know that sign is not that important, whether it is positive or negative. The behavior of the material will be same. So that's why we will not be interested in absolute value of the sorry, we will be only interested in the absolute value, not sign. So if we optimize the tau m square, it will work for us. So that's why we'll optimize the tau m square, and here that is found out using this relation. Sorry, this one will be Tm, not this is again a typo. Tau m square is equal to traction vector square minus sigma x square. So this is a typo, and the traction vector is this one. We can verify. So sigma 1 square m1 square. This is traction vector, and here there is some mistake in the sigma m square. I'm sorry that I have not checked it. So sigma m square, you can but other things will be correct. So here you can sigma m square you can see what we got in this case. So that's what you have to put here. It is sigma 1 m1 square plus sigma 2 m2 square plus sigma 3 m3 square. So that's what it will go. This sigma m, the same sigma m will go here. So it will be this. So sigma 1 m1 square plus sigma 2 m2 square plus sigma 3 m3 square whole square. So because it should be dimensionally correct. So now because when I saw the sigma 1 square and again whole square, I thought there is some mistake because it was not dimensionally correct. So there is a mistake in this, but I think rest of the things will be okay. And again there is a constraint equation, and you've just used the similar method to reduce this 3 variable problem to 2 variable problem by using this constraint equation. And then you differentiate with respect to m1 and m2, and we'll get two equations. And from those equations, if you see that the first solution, if we choose the first solution, we'll get this as a solution. So one extremum values will be along the principal direction, and we know that along the principal direction the shear stress component is 0. So the tau equal to 0 will be a one extremum values. So because we are optimizing tau square, so tau square is always positive, and in some places we have 0 value, so that means the minimum definitely has to be 0. So that's what it is coming here, and the other non-zero values will get non-zero extremum values we will get from the second equation. If you carefully see, the second equation will give the solution as this. So one solution we will get at 1 plus minus 1 by root 2 n2 plus n3. So and the second equation is, so it is like 45 degree between n2 and n3, and the second one is 45 degree between n1 and n3. The third one is at the intersection of n1 and n2. And if we use these values, we will see that magnitude of the shear stress will be on these planes. These three values you will get. Now we have not chosen or specifically given any choice to the sigma 1, sigma 2, sigma 3. Now we can arrange them in a fashion such that sigma 1 is greater than sigma 2 greater than sigma 3. Then we will see that the tau max will be, because we have these three values, and the maximum tau max will be 1 by 2 times sigma 1 minus sigma 3. So it is the half of the difference of the maximum and the minimum normal stress. So that's what that maximum shear stress magnitude, and it occurs along the plane of this one. So this is the value, middle one, if we assume sigma 1 greater than sigma 2 greater than sigma 3, and we will see that along this plane, plus minus 1 by root 2 n1 plus minus 1 by root 2 n3. So this gives 4 such planes, right? So along these 4 planes, because here actually comes as a complementary part, so we will get 4 such planes where this shear stress will be maximum. And on that plane, we will see that the sigma max will be having values of average of this the like sigma 1 plus sigma 3 by 2. So it is the maximum normal stress, the maximum principal stress plus minimum principal stress by 2. Okay, so we can understand this by seeing a picture here. I just want to show you this. So let us just look at this figure. Here you can see there are three principal directions, n1, n2, and n3. Along n1, sigma 1, along n2, sigma 2, along n3, sigma 3. These are the three principal stress values. And then if we arrange this sigma 1 greater than sigma 2 greater than sigma 3, then the plane associated with the maximum shear stress will be as shown in the as the hatch section. So it is 1 by root 2 n1 plus n3. So 45 degree between n1 and n3. And here I have just shown only one plane, but there will be four such plane. So because you can see n1 will be along this negative side also. So it will be going from this to that, and then and then the 45 degree plane from minus n1 and n3, and n1 and minus n3, and the 45 degree between minus n1 and minus n3. All this will give the tau max maximum as sigma 1 minus sigma 3 by 2. And on this plane, the normal stress value, normal stress component will be sigma 1 plus sigma 3 by 2. So that's what we have obtained for the extremum values of the normal stress and shear stress. Now, what I want to give you some Matlab demonstration to see how we can understand that extremum values. I will share this code with you. You can also run this and check yourself. So let me pull that. So here what I want to do is let me bring this picture. So let us say I have one unit sphere. Okay, so a sphere whose radius is 1, and then I'll just take each point, and on that each point on the surface of the sphere, and if I draw one vector from 0 to that point, so that unit vector will represent a possible direction, very possible arbitrary direction, right? So if I take all such points on the sphere, so we'll possibly consider all possible planes along the 360 direction. Okay, so I'll use a Cartesian coordinate system xyz to represent unit vector along this direction, any point on the surface. So using the spherical coordinate system, you can see the z components will be r cos theta here, whereas r is 1, so because it is unit circle, so it is cos theta, and then the projected line on that plane is sine theta, and that will have two components along x and y. So x components will be then sine theta cos phi, and y component will be sine theta sine phi. So we'll consider this spherical coordinate system to represent all possible normal vector, and then we'll choose a stress tensor and try to uh, get the normal and shear stress components on uh, on the plane which might have all possible directions along the 360 degree, and we'll see what values we are getting. Okay, so that means we are trying to take all possible planes by rotating it along the 360 degree direction, and we'll see what magnitude of normal stress and shear stress we get. So let us just run first. So this is how it is done. So I am taking some number of points, 50. So we'll and then theta is defined along you can see theta is going from 0 sorry, minus, okay, maybe here in the code theta and phi has changed, but okay, let me run. Maybe there is some change of theta and phi because phi is going from 0 to pi, and theta is going from 0 to 2 pi. Yeah, that's fine. I think it's following this. So here what yeah, here theta is going from 0 to pi, so that means from here to here 1/2, and then phi is rotating full, so that with that actually you'll be able to get all points. Okay, so if, that's what it is done here, and then I'm just plotting all this along this. Let me to show you what I get. I'll just comment this for now. Comment, and if I run, you can see that. So I'm just showing it a little bit. You can see I have got all possible points on one unit sphere. Okay, so this points represents a normal vector because it's the length from the origin is 1, so it's a unit vector, and they can represent normal vector along any direction. Okay, all right, so now let's see what else we have in this code. Now let me uncomment this portion. So here I'm defining one stress matrix as having diagonal values 2, 16, and 6. That means I'm taking principal values at 2, 16, and 6. With the known value we will start so that the values what we get from our exercise interpretation will be good. Okay, so you can start from any arbitrary stress values also, but if I take arbitrary, then the values what we'll get also will become arbitrary, and we will not probably understand it properly. Okay, so after that, Q is taken as orthogonal, because Q matrix, we know that if we use a transformation matrix, then it should be orthogonal. So orth is the command which defines orthogonal random, and randn is the random matrix. Okay, so and then Q transpose should be identity. So to show that, I've just multiplied Q star Q transpose. So this should be identity. That will prove that. And then SA is some transformation to that coordinate system, Q transpose SQ. So we are starting from a principal value direction, and then we are changing to some arbitrary direction. So that SA will be then having all 9 components. And then we'll find out the eigenvalues of that matrix or that tensor, and we'll see that that will have eigenvalues, mostly this 216.6. And from there, if I try to go back to our present S, the coordinate we have started, then we can again go back using the eigenvector matrix. This V is eigenvector matrix. This EIG is eigenvalue command in Matlab that gives both eigenvector V and eigenvalues U. And the SD is again the transform matrix from SA to the coordinate system used using the eigenvector matrix. So let us run and see what we are getting. Okay, so I'm not interested in the figure now. Let me see. Okay, we have start S using this. Q is some orthogonal matrix. Then you can see QT is 1 1 1, and this minus, but these are actually 0 because it is numerical value, so it will have something minus 0.00000, very large number, like uh, many numbers, many zeros will be there in that. And then SA is defined using this Q matrix. So this is some arbitrary the trace tensor transform to some arbitrary coordinate system, basis vector. And then this is the eigenvalue results of that new SA. So this is the eigenvectors 1, 2, and 3, and these are the eigenvalues. So you can see it is giving the same eigenvalues 2, 6, and 16. So that means the eigenvalues doesn't change. So whatever coordinate system you choose to represent the matrix, so this is the tensor, same tensor, this is also the same tensor, representing a different coordinate system. Their eigenvalues are same. Now if I use that eigenvector matrix to like transform from the SA, then you can see that we are going back to the diagonal matrix here. So the interchange can be done. So if I start from one, I can go to another one. I can start from there, I can come back to this one. All right, so with this, now let me see what I have. I'll uncomment this. All right, so here now for each of these unit vectors which I have defined, like for each of the points, data points there on the points on the sphere, we'll define n as the vector defined by x, y, and z, and then traction vector for that vector is SA. So I'm taking that arbitrary tensor SA. We'll work with that arbitrary tensor. The tensor with respect to some arbitrary coordinate system, to be precise, and then traction vector is SA times n, and then sigma is n transpose t, n dot t, and then tau is square root of t dot t minus n dot t square, sigma square. So sigma and tau is calculated. Now I am plotting this sigma and tau, but now you can see I have three coordinate system x, y, and z, and I have another values sigma. So we cannot plot a two-dimensional setup. So or maybe like we can plot some function with respect to xy, so to get a surface. But here I have three coordinate system and one dependent variable sigma, and three independent variable x, y, and z. So the plot we cannot show here. So that's why what I'm doing, I'm plotting sigma with respect to x, y. So that means every point is actually projected to the xy plane, and then for each of this point I'm showing a surface plot of sigma. So for each of that point, would be the sigma that is plotted. Okay, so let us first plot that and see what we get. Okay, so this figure 2 I'll just comment because it is for this one. All right, so let me run once more time. All right, so this is what I have got, and let me rotate and see what we have got. So now you can see this this is a very complicated surface, and if you look at this surface, the values are having three extremum values. If I just plot in xy, we may not see anything because that's every sigma is projected there. Xz, if I see, I'll see that there are some extremum values at 16. So there is a change of gradient at 16. So that represents one extremum values. There is a change of gradient at 2, and there is also change of gradient at 6. So remember, I had started with 2, 6, and 16 at the eigenvalues or the principal values, principal stresses. So definitely we'll see that these are actually representing some extremum values. So we proved that the principal stresses are the extremum stresses, so that we can show it using this example. Here also you can see 16, then 6, there is a curve like the gradient change, and at 2 also there is some gradient change. All right, so now let us see what is the plot for sigma, sorry, the tau, shear stress. Okay, in this plot, we can see it will have 0 as the extremum values, So here it is going to 0, and there are some values. You can see there is gradient change at 7. 7 is 16 minus 2 by 2. So we know that sigma will be the shear stress will be maximum at sigma 1 minus sigma 3 by 2. So sigma 1 was 16 and sigma 3 is 2. So it is 16 minus 2, that's 14 by 2, 7. And another extremum values will be sigma 1 minus sigma 2. So 16 minus 6 by 2, which is 10 by 2, 5. So this is where you can see one gradient change here, 5, around 5. You can see here in this picture. Okay, so 7, 5, and then another one will be 2. So you can see not 2, it is 6. Yeah, 6 minus 2 by 2. So 4 by 2. So you can see by rotating this one. So there is one gradient change happening at 2. So this proves also the extremum values of the shear stresses. Okay, this is a very complicated surface. So because ideally the surface is like this, should be sphere, and on that sphere, if I plot every point, if I plot the magnitude of the shear stress, then we'll get a complicated, like some surface over a sphere. So that should be the ideal surface, but that we cannot plot in MATLAB. So I'm just projecting these points to xy plane and then showing the magnitude of the shear stress and normal stress. Okay, now let me plot the third one. So in this third figure, what I am trying to plot is let me just comment this too, already done. So here I'm trying to plot sigma versus tau. So x-axis sigma and y-axis tau. So whatever sigma and tau I have got, if I plot for like each sigma, what is tau, that means x-axis sigma and y-axis tau. And then this axis image means it should make a equal axis length along x and y. So the reason for that you will see very shortly if I. So let us run this. Yeah, so now you can see what I have got. I have got 3 semicircles here. So once the smaller one and another 2 smaller and 1 bigger, and each points the sigma tau actually outside the smaller 2 semicircles and inside the larger semicircle. So that's very interesting. So each points will lie within the 3 circles. Okay, 2 smaller circles and 1 bigger circle. So this is called the Mohr circle of stress. So in 2-dimensional case you got only 1 circle, but here for 3-dimensional we will get 3 circles. And for 2-dimensional case, you know that the point of sigma and tau along different planes will lie on the circumference of the circle, but here the points on different planes, the normal stress and shear stress on different planes, will be within these 3 circles. Okay, so inside the bigger circle and outside the smaller circles. The mathematical proof of this is there in the next discussion, but let us stop here for time being, and then in the next lecture I'll show you how mathematically we can prove this. Okay, we have seen from the MATLAB calculation, but some mathematics also will prove this, that sigma and tau will be like this. Okay, all right, so I'm stopping here.